Hello, AP Chemistry students. This is section 3.13, which is the last in Unit 3 on the Beer-Lambert law. So our learning objective here is to explain the amount of light absorbed by a solution of molecules or ions in relationship to the concentration, path length, and molar absorptivity. So I talked in the last one about spectroscopy and how a spectrophotometer is used to shine light through a sample in order to learn about its physical properties by way of how it absorbs or transmits light. And in this sort of setup, if you recall, we have a light source that is a combination of a bunch of different wavelengths that is shown through a monochromator, which is kind of like a prism that separates out all of the wavelengths into their individual parts. And then those are shined through the sample one at a time, and then they hit a detector and give us a reading. And the absorption of light is measured indirectly by way of the percent transmittance. So what that means is how much of the light gets through, what percent of the fraction of light that is transmitted over the light that was shown through in the first place. And then it's multiplied by 100 to turn into a percent. So at the end of a spectroscopy experiment, you usually end up with a spectrum, which is a relationship between the absorbances of different wavelengths. And you're going to see peaks that corresponded to wavelengths that were absorbed by that substance. So in whatever this graph is, we see that we have three peaks here at 443, 471, and 502, and then a really, really small peak here at 360. That's telling us how many photons of light corresponding to that wavelength are being absorbed. And this can give us a lot of opportunities to both identify and analyze different samples. So the intensity of absorbance is usually relative to the concentration. Because the higher the concentration, the less light is transmitted. If you think about the light passing through a sample here, the more stuff there is within the path of the light, the more chances there are for the light to interact with the sample. So the more particles there are, the higher the absorbance is going to be, and the lower the transmittance is going to be. And we can end up getting something like this. So you can see here that this is the same spectrum. And if you look really closely, it says milligrams here. So this is showing the absorption of a sample at these two specific wavelengths as a function of concentration. So the less stuff there is in the solution, the less absorbance we see on the y-axis. But we still see the same wavelength of absorption. And we can use this to our advantage to study unknown concentrations of samples, because what we can do is create a collection of solutions with known concentrations, which we call standards, and we measure their absorbances at a specific wavelength. So we choose some wavelength where they have a lot of absorption. So say we were doing this last one, we'd pick a wavelength here and measure its absorbance at all of these different concentrations. And then we can graph our data and get something like this, where we have concentration on the x-axis and absorption on the y-axis. And we can see all the different absorbance values associated with all the different concentrations that we made. And you can see that you end up getting a linear relationship, which can be graphed as a y equals mx plus b type equation. And this y equals mx plus b equation is actually called the Beer-Lambert law, also commonly referred to as Beer's law. And this law states that the absorption A is going to be equal to epsilon BC, where A is the absorption. It has no units, so all the units are going to cancel out in this equation. And this is the detected absorption from the spectrophotometer. And then we have epsilon, this like E looking symbol. This is called the molar absorptivity. And it's measured in inverse molar times centimeter. And this is a constant that's specific to the substance that you're studying and specific to the chosen wavelength of absorption that you chose for your spectrophotometry experiment. And this relates to how intensely the light of that wavelength is being absorbed. So the higher the molar absorptivity, the more light is being absorbed, and the higher the value for this constant. And then B, which is also kind of a constant, is the path length. And this is how far the light travels through the sample. And a standard container for this type of experiment, which is called a cuvette, is 1 centimeter long. It looks a lot like this type of thing. So the path length is the length that the light passes through the sample. Okay, and then lastly, C in this is the concentration of the sample. And this is usually going to be in molar or whatever units the constant is. The units need to agree because the molars are going to get canceled out and then the centimeters are going to get canceled out to give us an absorption value that has no units. So overall, absorption is equal to the molar absorptivity constant times the path length times the concentration. And this maps to our y equals mx plus b equation. Because if you recall, the y on the graph was the absorption and the x on the graph was the concentration. So the a is equal to y and the c is equal to x. And then for the m, the slope of the linear relationship, it's going to be equal to epsilon b because b is just 1 centimeter. This is just a constant. So whatever the slope of the line is going to tell us what our molar absorptivity is at that measured wavelength. And then the b value, the y-intercept in the y equals mx plus b formula, is sort of like an error factor, since it's going to measure how linear the relationship is and if it passes through the origin. Because in this type of experiment, even though you made a bunch of concentrations, known concentrations of the substance that you're studying, you're always going to want to record a 0 concentration one as well. That's just whatever the solvent was. So if it's just like pure distilled water, so you can get sort of a background reading that you can set to 0. And that'll hopefully make the rest of the relationship more linear. So you're always wanting a pretty low value of B if possible. So once the Beer-Lambert law has been determined for your experiment, you can use it to solve for a concentration of an unknown by measuring its absorbance. So say we had that blue substance from before. We measured all those different concentrations. We got a linear relationship between them. And then we also derived a y equals mx plus b formula so we can determine what the relationship is between the absorbance and the concentration by way of the slope, which is our molar absorptivity constant. So we don't know the concentration of an unknown, but say we plug it into the spectrophotometer and we get a reading of 0.1250. Well, we can use our equation to sort of infer what the concentration is going to be mathematically. So if the y is equal to, in this case from the graph, 2071.9 x plus 0.0111, we can plug in our absorbance value for y, and then we can solve for x, which is going to be the concentration. So we plug in y, and then we end up solving for x, and then we find out that our unknown has a concentration of 5.497 times 10 to the negative 5 molar, which makes a lot of sense if we look back at our graph. If we had a concentration around here, yeah, it's going to be around 5 something times 10 to the negative 5. So we're going to be doing a lab on this week, and we're going to measure the concentration of blue dye in a bottle of Gatorade using standard samples of blue dye with known concentrations. So I'll see you in Unit 4.